Well, hello there and welcome back for more Advent of Code. So, let's see where we were. Last day that we solved was 23 and it was a very challenging one. And we are now on day 24, almost at the end already. Very nice. So, day 24. Never tell me the odds. The odds? It seems like something is going wrong with the snow making process. Instead of forming snow, the water that's been absorbed into the air seems to be forming hail. Hail are like pieces of ice, like ice rocks. Look at that. That's a very sizable piece of hail. Maybe there's something you can do to break up the hailstones. Oh, very nice name, hailstones. I didn't remember about that word. Due to strong, probably magical winds, the hailstones are all flying through the air in perfectly linear trajectories. You make notes of each hailstone position and velocity, your puzzle input, for example, this, so I guess this would be positions and the velocities. Each line of text corresponds to the position and velocity of a single hailstone. The positions indicate where the hailstones are right now at time 0. The velocities are constant and indicate exactly how far each hailstone will move in 1 nanosecond. Oof. They're going fast, although we have no units for this, so maybe they're super slow. Each line of text uses the format px, py, pz at vx, vy, vz. It's missing the commas here though. Interesting. Maybe just an editorial mistake. For instance, the hailstone specified by 2019-15 at 1 minus 5 minus 3 has x position 20. Okay, yeah, very self-explanatory here. After 1 nanosecond, the hailstone would be at 21, 14, 12. So yeah, adding these velocities to these positions. Okay, seems like a physical kind of puzzle, this one. Perhaps you won't have to do anything. Okay. How likely are the hailstones to collide with each other and smash into tiny crystals? To estimate this, consider only the x and y axes. Axes? Is this the plural of axis? I didn't know. Ignore the z-axis. Oh yeah, so axis is singular with an I, and axis with an a, with an e. Sorry, is plural. I didn't know that. Looking forward in time, how many of the hailstones' path will intersect within a test area? The hailstones themselves don't have to collide, just test for intersections between the paths they will trace. Okay, so like line intersections? In this example, look for intersections that happen with an x and y position, each at least 7 and at most 27. At least 7 and at most, okay, that happen with an x and y position. Okay, so within a given area. In your actual data, you'll need to check a much larger test area. Comparing all pairs of hailstones, future paths produces the following results. Okay, so we have combinations of hailstones A and B, so I guess these are all the pairs that can be formed for this. Hailstone's path will cross inside the test area at... Ooh, look at that, we have numbers with decimal parts. I think this is the first time I see something like this in Advent of Code. So will this be the first time that I use floating points for this? Interesting. It's always called A and B, so I guess we are using, we're comparing the first one to all the others, I guess. So we cross inside the test area. Hailstone's path will cross outside the test area at 6.2 and 19 Wait, isn't this? Ah, no, it's from 7 to 27, so 6.2 is out. Hailstone's path crossed in the past for hailstone A. This is interesting also, so we have to take into account the direction of the velocity, which makes sense, I guess. Like, not the direction, but if it's forwards, yeah, if it's forwards in time, the moment that they cross. Hailstone's paths are parallel, they never intersect. Ooh, yeah, so look at that, -1, and -2, -2, so they are parallel in the xy, and also on the z. This goes at twice the speed, but doesn't matter, they are parallel. Cross outside the test area. Cross in the past for both hailstones. Outside. Pass for hailstone B. Okay. So in this example, 2 hailstones future paths cross inside the boundaries of the test area. Okay. However, you will need to search a much larger test area if you want to see if any hailstones might collide. Look for intersections that happen with an x and y position, each at least 2 and I don't know how many zeros, and at most 4 and lots of zeros. Disregard the z axis entirely. Considering only the x and y axis, check all pairs of hailstones' future paths for intersections. How many of these intersections occur within the test area? Okay, kind of a weird puzzle. Well, mostly weird because it's like it's using numbers like non-integer numbers for solutions, which is kind of a first time I think I've seen this. And look at that, the positions are quite big. Okay. So I guess the first idea will be to try to implement this for the sample. And I have to remember how to do some algebra and find out the intersection between 2 lines. Yay, that sounds fun. So let's jump into the code. And I have local changes, I don't remember why. What are the local changes? Oh yeah, probably the readme, yeah. An outdated annotation note from the previous session, which by the way, I really enjoyed I'm really satisfied with the solution for day 23 after all of the work and refactoring, and I actually simplified it a bit further from what I recorded in the previous video. So this is the build graph function that it had a very nasty switch or match statement, and now it's just 2 cases handled with a single if. So it's a bit, I think, yeah, a bit better. Like only one case is when you keep walking, and another case is when you're on an intersection, and it still works and it's very nice. But we should be talking about day 24. So day 24, it was don't tell me the odds. Don't tell me the odds. It's also a very odd name. Don't tell me never tell me the odds. Never tell me the odds. Why is it called like this? Oh, okay, so the odds of like hailstone collisions, I guess, or something. And this puzzle is also one of those cases where the sample has it has a different condition than the actual input. So here we expect, like, I don't know if I will commit this sample because the test area for the sample and for the input are different. And well, I will either have to special case the code for that, or I don't know, do something else. So we have 300 hailstones. and all the combinations, it will be 300 times 299, right? So 300 by 300, which is watts. It's 9, and for zeros that is 90,000. Not too much, it's fine. Okay, we can close everything else. We can close the sidebar, bump the font size, and think. So I have to find intersections between lines, and my algebra for this is very rusty. So should I Google for that, or should I try to, maybe I can try to make some annotations for this and see if I can figure it out on my own, but I'll try to not get too lost and not go too much into a rabbit hole. So if I cannot make it, I will Google it. But let's see how my algebra skills are still in place. So this is basically, these are lines that start at this position, and well, this will be like the derivative of those lines, or well, the direction of those lines. So you can think of, for example, and also we can ignore the Z axis entirely, so that's fine. I don't have no idea what part 2 will be about. Apparently all hailstones are falling down, which is nice. Nothing is falling up in the sky. Oh, but look at that, in the actual input there is one that is falling up. Yay, very nice. And it's not the only one. There are many others that are falling upwards, so that's interesting. I don't know if like part 2 will be about a volume of area or what, but it's interesting. And also, like, for part 1 we are only computing if the paths cross in the future, but that doesn't mean that the hailstones will collide, because they can be going at different speeds, or like one could cross and then the other one. So I guess the probability of colliding will be very, very small, and only one pair of hailstones will collide. That would be something like Advent of Code for part 2. But okay, let's think about part 1. So how do we define two lines? One way of defining a line is like with an equation of saying a line is like the typical case of saying like expressing the y coordinate as a function of x, so saying something like a times x plus b, and this would be the equation as with y as a function of x. But there's a problem with this, which is that what if your line is parallel to the y-axis? So, for example, the equation x equals 5. This is an equation of a line, and it basically is, well, a line that goes crosses x at 5, and it's just a vertical line, which you cannot express like a function of x. So I don't think so, because if we had something like this, we could say, okay, this is like the line 1, for hailstone 1, and you can say, okay, for hailstone 2 would be a similar thing, but with other constants, so x times c times x plus d, for example. And then you want to solve for, you know, x, the same x and y. I don't know if that would be solvable. So maybe you can try something like this. So if you have, this would be like the equation for line 1, and this is the equation for line 2. And if you do 1 minus 2, or yeah, I guess 1 minus 2 could be a way to express it, or, well, you can, since the y's have to be equal, this is the same as saying, well, yes, we can think about 1 minus 2. So you have ax minus cx plus b minus d. All of this will equal 0. And then we can solve for x here. So this is the same as x times a minus c plus b minus d equals 0. Typing math on a keyboard is so fun. And then x, we can say that it is d minus b, and this is where I surely will make a mistake. All of these, remember the parentheses, divided by a minus c, and this assumes that a minus c is non-zero, right? Would this be okay? And then with this, you can find the x where these two cross, and then put the x in one of these and find the y, right? Would that work? When they are parallel, how you find out about that? Is that the case where this is like, how do you find that out when they are parallel? Okay, so let's think about one of the examples, because we have examples for this. So let's copy these two. So the equation for hailstone A, for instance, in this case would be y equal, so sometimes something, how do we find this actually? I don't have these things expressed like this, so we have to find, yeah, this is not the way to go, I think. Already messing it up, I think, because there is another way of expressing, and I should have paid attention to that example of like a vertical line, like x equals 5. Okay, let's keep this example that we want to test, but there is another way. Let's forget about this. There's another way you can think about a line equation, and it's like with vectors, which is much similar to what we have here. And I think when you think about vectors, you don't, instead of like expressing it as a function, like y is a function of x, you don't have to worry about that edge case of the line being vertical, I think. So generally, a line expressed as a vector, you can say something like xy, like all the points on a vector, all the points xy on the line are of the form an initial points that you know that the line crosses. So I don't know, x0, y0, and these are vectors, kind of in a weird notation, plus, and here I'm going to express this as what we have here, so like it makes sense. X and y would be like positions, and these are velocities. So let's say that vx is the velocity on x, and vy, all of this times a, how do you say, like a factor t. So t is the thing that varies. It's kind of like an equation on t, or a formula on t. So t, you vary this thing and you get all the points on a line, basically. I don't know if this is the best way to express this, but it is like we can do this with these numbers. Okay, so that makes some sense. If we have like line 1, kind of what we did here, 1 and 2, like line 1 and line 2. Line 2 will also be something like this, but it will have other numbers. So it's a bit annoying to call this. So let's call x1, y1, and vx1 and vy1. Beautiful, beautiful names. This is the same with 2, and you would have like another variable. You can also call it t, but I want to, like this can vary tv, you say, like another variable to move there. And again, we can make this thing equal this to find the intersection between these two things. So it will be this equals this, and we can solve, I guess, for t and for v, right? Kind of. And we will have you can write this as a vectors or as each of these. Wait, don't I have like too many equations if I do that? Because we have like two variables, and I think we would have like a system of 4 equations. So something is, I'm missing something here. If I want to expand this would be, well, let's write it, let's use the power of copy paste to start with. So beautiful, right? We can say that this is equal to this, and if we expand the x and y, I guess, no, these are not, so this is basically, okay, like one equation that we can separate into 2. So you have like x1 plus t times vx1 will be equal to x2 plus v. V is kind of ugly. Oh, and look at the formatting. Come on, don't do this markdown. Don't do this. Let me copy this and move it to a new document, which we just call notes txt. Don't format anything. Where was I? So x2 v times vx2. So this would be like our first equation. I guess we can also like move everything, since it's an equation of 2 variables. We will have to, okay, so we will have something like this, and also a very similar thing, but for the y coordinates basically, and same shape of things, right? And then from these 2 equations you would have to find, I want to like at least try to see if I can solve for one of the example pairs, and then I can Google things and see how math is, if math is still in my head or not. So okay, we can express these 2. Let's actually like combine these 2, right? Is there a way that we can combine that would leave us with x and y, like only with t, and get rid of v, for example? Surely is, but math skills are a bit rusty, to say the least. Okay, so if we solve for t on the first one, we will have like x2, well, this thing, minus x1, I think I probably should group x1 and x2 on this, but anyway, all of this divided by vx1. And yeah, my problems also with this is that what happens if these are 0 and you cannot divide? It's like you can also solve in the t on the other equation in that case, but there surely is a way to combine these two or something. Screw it, let's Google. no Rust. Two lines intersection. Woohoo! Yes. Line and line intersection. That sounds like the Wikipedia article that I want. Yes, in Euclidean geometry. Yes. Given 2 points on each line. Oof! Look at that. Are these like matrix determinants or something? So consider the intersection of line being defined by 2 points, x1. Okay, so these are lines defined by pairs of points, which is kind of what we have. We can do the position plus the velocity to get the second pair, sure. So okay, I think this notation is like determinants of matrices, right? What a complex thing, but then the determinants can be written out as... Yeah, this is something about geometry or algebra that I don't really remember, like determinants and stuff like that. Like, I don't know if I ever actually knew about this. Given 2 points on each line segment. When two lines... Oh, look at that. When two lines are parallel or coincident, the denominator is 0. This is kind of what I want. Yeah. Intersection geometry, 2 line segments. So that's another that's another article. Interesting. Intersection. Oh, look at that. This is more similar to what we were doing. Yeah, in fact, it's line 1 is like it also used t for the time, but it used u for the other variable, which makes sense. T, u, v is the order that the alphabet goes. I don't know why I picked v. I don't know. But okay, and usually t is used because it's like it represents time, right? Numbers, the intersection point of these lines is found with one of the following values of tu, where t is again like a determinant thing. So here it's doing x2 minus x1, which is kind of the same as saying like the velocity. This x2 minus x1 is the velocity of the first line, or well, yeah, like the direction of this. So that's also nice. And I have no idea why it's crossing like x1 with x3 that is from the other line. So it's probably doing this equation minus this, or something like that. But okay. And then you can find, if you find t and u, you can then find the intersection points, right? Using t for the... it's like you can find t or u, and then you get the intersection points using either of those. There will be an intersection if t is between 0 and 1. Yeah, it makes sense because this is a line segment, and I think we should use something like this because we can compute these two values, t and u. We will need to compute both, I think, and then see if they are both positive, which will mean like that the intersection is in the future, I think. This is for two line segments, so it goes from 0 to 1, so that's the parameter parameterization of the line segment. But if you say from 0 to infinity, it's like just saying from point 0 till the future. So I think something like this is what we want. It's kind of an early formula, but... And these two line segments... There's not necessarily intersection points, because intersection... Yeah, okay. In order to check the situation, one uses parametric representations of the lines. Yeah, so this is kind of the... It's expressing x as a function of s, and well, x and y as functions of s. Yeah, this is kind of what we wrote, similar to it. Intersect only in common points. Yeah, okay, so this is saying basically the same as the other article, I think. The solution. Linear system. Can be solved for S and T using Kramer's rule, or Kramer's rule. Kramer is the character from Seinfeld. Oh, okay. So in this article, you have the case for two lines and two line segments again, for some reason. So line intersection is one article, and intersection geometry is another. So what is Kramer's rule? Okay. I think this is kind of the more general equation for a line that I didn't think about. Instead of expressing it as y being a function of x, you just express it as an equation, and I think these are general. If a1 times b2 minus a2 b1 is 0, the lines are parallel. Yeah, okay. So it's kind of like this. And what is Kramer's rule? General case. Oh, here's the determinant things. Okay, this is, I think, too much algebra for me. Do you have like a simple geometric interpretation? Yeah, this is too much mathematics for me. But don't you have like, wait, Kramer's rule, doesn't this have like a case for two variables? Like it should, right? Inverse matrix, explicit formulas for small systems. Okay. Oh, okay, it's kind of, yeah, this is what I was looking for. Yeah. Okay, so if you have a system of equations of these forms, then you can find x and y using this. So I guess this is like the Kramer's rule for a system of two equations and like a specific case of that. And you also have three equations, and maybe we will need this for part 2, but for part 1 it seems easy enough. And okay, so for the case of the parametric formulas, okay, so what you're doing is line segments. Yeah, the parameters T and solutions of the linear system. This thing is coming from s times x2 times. How is it coming to this linear system though? It's doing some algebra on these things. So here you have, yeah, I think it's just making these two things equal. Not entirely sure how it's coming to this though, from these two equations. Like you can make these two things equal. Oh no, yeah, it's just the first part of this equals the second, like the first part of the second one. Yeah, and this mixes S and T, yeah, and you have this here. What did I write? Didn't I write something kind of similar? Probably not. You have this, yeah, it's kind of, not quite, almost. Also because x2 minus x1 is like the velocity of the first line, and x4 minus x3 is the velocity for the second line, so it is kind of what I wrote here. Although I had to, yeah, if here I put T and V on the same, yeah, if I rearrange this, T basically, let's copy this. I can rearrange this, passing this to the other side, minus, and then this to the other side, and I shouldn't say passing, I should say like, okay, subtracting this from both sides and blah blah blah. But here this is now the same shape as this, if I'm not mistaken. The variable names are a bit confusing, but yeah, I think I was using x2 for the second line, and here is using x3 for the second line, but yeah, and these velocities are these subtractions here. So from this, it can be solved. It says it can be solved for S and T using Kramer's rule, but it doesn't give me like the solution. So I have to apply Kramer's rule, or in the other article, I guess I have the solution, which is this. Yeah, right, this looks like it. Yeah, this looks like it. It looks like the same variable names and stuff. Some things of these are like our velocities, and these are the differences of our guys. So okay, let's maybe copy one of these, because I think I will just use the velocities that we are given, and instead of computing like the second point and copying exactly the thing from Wikipedia, because I think we could get away with that. So in our case, T is going to be, it's an ugly thing. So x1 minus x3 is the same as, why is it though, no, x3 minus x1, maybe, I'm a bit suspicious about this. Should I bite the bullet and try to follow Kramer's formula for this? I think I can. I think I should be able to do it. No, I didn't want that. I wanted this. Okay. So let's see. We have this, and we have to get to this. Confusingly, x and y here are our t and v, which is a bit confusing. And c1 and c2 is this and this. So we have to like mentally do that. C1, so we try to write this, which is like the solution for x, which x in this case is t. We are subtracting here, so in order to write this down a little bit better, I would say something like plus minus, this thing, I think. I don't know if that makes a lot of sense. Should I rewrite this somehow? Okay, let's try. So I'm trying to do this basically. C1 is going to be x2 minus x1. Then B2 is the coefficient, this coefficient, basically the speed that we have here. So this is going to be times minus Vy2. Beautiful. Times minus Vy2. Not very pretty already. We could put, yeah, since this is times a negative value, we can turn around x1 and x2 here, and that would be the same, right? And I'm already changing things up. But I think this would be the same. Then we're gonna do minus b1, which is the coefficient of the first one, so vx. No, I have to look at this. The b1 is the coefficient, yeah, the second coefficient of the first one. So again, this is minus vx2 times c2, which is this. Don't miss the parentheses. And since this is again minus, we can apply the minus here, and it turns this around, I guess. Okay, this would be it, and we have to say over, so divided by, and we're gonna parenthesize everything, yes, and then divided by, and on the bottom part we have a1 times b2. So a1 is the coefficient of this, so vx1 times b2, which is the coefficient of this, which is minus vy2. Why do I have this minus? Yeah, this is kind of ugly. Not sure if surely is an algebraic way of fixing this. Maybe like, yeah, if we multiply everything by minus 1, we can turn, I'm not sure. Let's keep it at this. So vx1 times b2, so b2 is this, so time minus vy2, all of this minus b1, which is minus vx2 times a1, which is no, times a2, sorry, which is vy1. And that is a mouthful. And this is a negative thing. Minus, like, there is surely a way to simplify this. Two negative things, so this is the same as multiplying by minus 1, and so we can take the minus 1 out. We can say minus everything, and minus everything is like turning this 2 around, I think, right? This is the same as, yeah, distributive. We distribute the minus of all of this, and then if you have minus a minus b is the same as saying b minus a. So I think if we turn this around, this thing minus this thing, and I surely with all of those changes I surely screwed it up. This was just the solve for for t, and then for v, it's going to be basically the same thing. The denominator is the same, which is nice. And the, okay, maybe we can write it if it's not too much. V, then, why did I choose v? It should be u. Like, that's the thing that makes most sense. So let's actually rewrite this as u and u here, and then solve for u. I'm taking these notes because I'm probably going to paste these things as comments on the code also. So the denominator, like, is going to be a giant thing divided by the same thing, and the giant thing should basically have a very similar shape to the one above. Unfortunately, I did those stupid like changes of shape, so now I'm not really sure. So now I'm copying from this. A1 is Vx1, so Vx1 times C2, and C2 is this thing. Sure, and all of this is going to be minus. I don't know why I'm not using correct spacing here. Now it's a bit better. And the minus is aligned. Minus C2, no, sorry, C1, this thing, times A2. So times, and what is A2? Is Vy1. Okay, so it wasn't that terrible to write. Oh, I missed the parentheses. Don't screw it now. Okay, so it is a thing. I'm not sure if I did it right. Maybe we can try to find t and u for this thing. Right? So in this thing, in this case, we will have x1 is gonna be 19, y1 is gonna be 13, vx1 is gonna be minus 2, y1 is gonna be 1, then x2 is gonna be 18, y2 is gonna be 19, bx2 is gonna be minus 1, this is so fun, vy2 is gonna be minus 1 also. These are not parallel, these are two that like I copied from the first case, and they will cross inside. You should see them cross inside, unless I screwed it up very badly, which is highly likely. So in this case, t is gonna be, so x1 minus x2 is 19. We can start doing the math, I guess. So 19 minus 18 is 1 times, let's actually copy this. Let's solve this part, which is the same as for both. So this is going to be vx2 times vy1. Vx2 is minus 1 times vy1 is 1. So this is minus 1. Minus vx1 minus 2 times vy2 minus 1. So this is minus 1 minus 2 times minus 1 is 2, so minus 1 minus 2. This is minus 3. Did I screw it up? I'm not sure. It's minus 3, right? Okay, this is the denominator. It's not 0, so no problem. They are not parallel. We already knew that, but it's good to check it. Now, t is we can copy this and copy that and start replacing. So x1 minus x2 is 19 minus 18. This ended up like this because we turned it around, right? So this is 1. by2 is minus 1. Oh, look at that, highlighting, awesome. This is also minus 1. And this y1 minus y2 is 13 minus 19, which is minus 6. And all of this is, like this was t, right? If I'm not mistaken. All of this is divided by this denominator, which is minus 3. So this is 1 times minus 1, so minus 1, let's write it, minus 1 minus 1 times minus 6 is positive 6, so minus 1 minus 6, this is all minus 7. So we end up with minus 7 over minus 3, which is, please, well, I can use, I guess, minus, well, it's the same as 7 divided by 3. Let's use floating point. 2.3, which is, this is the t, this is not, and we only need to actually calculate t, right? Well, we know that t is positive, so that's good to know. Let's also calculate u, because we want to see if both are positive, but this is not, it's not looking that bad. Now with u is this thing, and it's all of this divided by minus 3 that we have previously calculated. Now this is minus 2, y2 minus y1 is, so this is the other way around, y2 minus y1, 19 minus 13, this is 6, x2 minus x1, 18 minus 19 is minus 1, and by1 is 1. So this is now minus 2 times 6 is minus 12 minus minus 1. So this is minus 13 divided by minus 3, which again we can calculate. It's the same as 13 divided by 3. 4 times 4.333. Sorry, that was what I wanted to say. And now finally, we can get this is t and u, and we should get the intersection, which we don't have the formula here, but we have it somewhere. If you have t and u, you can have the formula like xy of the intersection is, yeah, this thing. So let's, this is x2 and intersection, no, this like the x and y solutions is gonna be yeah, x1 plus t times, I'm basically copying from here, and x1 minus x2 in this notation here is not the same as what we have, is the same as vx1, and the y coordinate is basically the same, plus, but using the, no, yeah, we're still using t times v y1, right? We are using everything from the, yeah, from the, we can use it from the first line or from the second line, it doesn't matter because it's the solution. So yeah, I want to make sense of yeah, this is basically what we are using now. This we can forget about. Yeah, this is kind of all the pertinent notes. So if we consider this, then the solution for the example case that we did, we can replace here, and x1 is 19 times t, which is 2 times 333. Vx1 is minus 2. Okay. And then y1 is 13 plus t, which is 2 times 333. And vy1 is 1. So this is, we can solve, we can maybe write it. 19 plus 2 times 333 times minus 2 is 14. Well, this is 333. So 14, 333, and 13 minus 2, 333 is 10,666. 10,666. Is this the answer? It's not. 14,333 it is. 14,333 was correct, but the other one was not. Did I? Oh, I think yeah, it was correct actually. 13 plus, I just made a mistake, the last, this was plus, not minus. Oh, I just did a stupid sign mistake at the end. Awesome. So this is actually 15,333. So yes, these stupid algebraic things that we did, and it's already been an hour in the video and I haven't coded anything, are correct. So, and I'm also a bit sweaty. It's a bit hot, even though today it was raining. I should drink hot tea to make myself a bit cooler. Okay, so we have checked that this approach at least works in theory, in paper. Let's try to do it in code. So we want to parse this thing as usual. We can get rid of this. Actually, parsing this should be pretty simple. Let's just do it like this, in the simplest way possible. We are going to have basically a bunch of numbers. And we want to compute. Let's just do let's hailstones. It's gonna be the input, as usual, input lines. Then we're going to map each line. Let's do the parsing right here, like right in the main. We are going to use our trusty function parse numbers for this line, and this should give us 6 numbers. And actually, these parse numbers, I think for negative numbers we are going to have a little problem, so let's try to wait and see. Wait, I said that I wanted this on a function inlined here, but I think I will extract it to a function. So yeah, let's call this thing, let's call here parse hailstones, passing the line, and then we're gonna, because I want to use like try collect here from iter tools, propagate errors up, generate this function, and this is going to be a result of AOC results of basically, yeah, 2 points, point and points, and let's define. Oh, wow, look at that! I didn't know that there was a. How did I do that? See, oh, that there's a nice test macro that I never knew about. But yeah, point is gonna be, and we're actually going to use floating points, right? So this is an first time I'm using this, but let's use 64-bit numbers just to be sure about precision. And let's here say something like let's, and we're gonna have the XY set and Vx, Vy, and Vz. We're gonna ignore the sets, but here I'm going to call AOC parse numbers for this, well, we can call it S, it's just a string. Let's call it actually numbers, and then we're gonna do numbers a bit ugly this, but iterate and then collect into a little tuple. Okay, and this should be the correct. Now they don't know their types yet, but once I return them and say, hey, okay, the first point is XYZ, and the second point is Vx, Vy, Vz. And you don't like this because, oh, this collect tuple can fail, but we can give this thing a context and say invalid line, propagate the error up. And finally, found string. What? This is a vector? What did I did wrong here? Numbers. Oh, propagate the result up. Okay. And I think I actually will have a problem here, and try collect cannot be. What is your problem now? Hailstones. Try collect. Oh, try collect into what? Into a vector, of course. So this would be a vector of hailstones. You can inline this because you like it, I know. And let's print out of this. So for stone in hailstones, print line, just print the stone as debug prints. Can I type something? Apparently not. So if we finally run something, binary for day, what is today? Day 24, inputs 24 sample. We did parse something, but I think the numbers are wrong. 19, 13, 30, it's okay, but then -2, you can see that it's 2 and there is no minus. And that is because in our stupid parse numbers function, we are splitting everything. So the idea of these parse numbers is that just ignore anything that is not numbers, like the commas, the spaces, the at signs and everything. Just parse whatever numbers are on the line. And we are splitting by things that are not ASCII digits, but we should also take into account minus signs. So let's say split things that are not, like value things are things that are ASCII digits, or So this is what I want to say, this, or the character is a minus sign. If we sort of apply De Morgan here and negate both of these, I think if we say, hey, it should not be an ASCII digit and not, if it's not an ASCII digit and it's not this, then we do something. And if we do this now, yes, we are parsing the negative numbers as we expect. And I don't know if the checks are still passing because I changed that thing. Well, yeah, the expectation for the last day is not passing, but that is to be expected because we haven't coded the thing yet. Yeah, and the other thing is also like printing a bunch of stuff. But it seems like the parse function is working now, like except for day 24, which is fine. Okay, so we fixed parse numbers to actually parse negative numbers. Great. So what's next? We have to code the line intersection. So we have to iterate over all the pairs and see how many of them cross in the future for the area that we care about, in the area that we care about, okay? So how do we do that? Yeah, if it is, well, let's just write it out and see what happens. So I'm just gonna say answer for part 1, or do we have like a better way? How many intersections occur within the text area? So yeah, intersections count. And we're gonna do hailstones. Can I do combinations? I think this is in the iterator thing. Tuple combinations is what I want. I want to count these things basically, right? So we are going to filter these combinations and we are then going to count, I think. So what are we going to filter? So we're going to have like the hailstone 1 and hailstone 2. So let's say H1 and H2, and maybe then say let's, and here I want to use the same names that I used for this. So X1 and Y1, yeah. So this will be X1, Y1, and ignore Z1, and Vx1 and Vy1, and ignore Vz1. This is the first hailstone, and same idea but with 2's instead of 1's for the second hailstone. Let's return false here so it doesn't complain in the meantime. And with that, we can compute T and V already, I think. Although we can compute the denominator first to see if they are parallel. So let's let me think a little bit. yeah, I would like to put some of this like in comments, but let's not worry about that now. Let's try to just get to the answer. So yeah, we're gonna get the denominator. That is, let's say, let's denom, it's gonna be this, and we can say if denom is 0. I don't know if actually asking for floating points like this, like 0 in floating points, makes sense, but I mean these are all integer values, so I don't think we are going to get into floating point shenanigans, so it should be fine. And this actually kind of makes a lot of sense now that I think about it. No, I don't know if it actually makes more sense, because it's like a cross product of the two. So that's how you sort of normalize the velocity, and then you subtract. Yeah, it makes a lot of sense. So with this, if this is the case, let's print actually, and say, well, I would like to print it parallel hailstones. Let's just print h1, print all the mess, and h2. This, you don't need parentheses, sure. And this is debug print, and then we're going to return false in this case. And you don't want to ask for 0 because and found an integer. Well, yeah, let's ask it like this. And let's actually run this to see if we find some parallel. Yeah, look at that. We have one pair of parallel hailstones, and I think it was only one, right, that was parallel? Yeah, only one of them is parallel. And do the 18, 19, 22 and 20, 25, 32. 18, 19, 22, yeah, and 20, 25, 30, 20, 25, 34. Also, awesome. So it seems like we found the parallel hailstones only once, and then the other ones are not parallel, so this is already somewhat promising. And then we want to compute t and u. So let's just copy this. Let's just copy this thing and say let t equal blah blah blah. This last thing is the denominator, and u is, well, this kind of thing. Let's u divided by denominator again. And what do we want to say? Basically that t and u are positive. So if t is the thing that we were using for like the parametric thing of the variable or whatever it's called for the first line, right? Yeah, for the first line. So let's actually maybe ask about that. If t is less than 0, then hailstones parse with, let's print this case also, print line hailstones cross in the, you know what, we can, let's do some printing, like let's do some extra printing. So A, we can print the hailstone 1, and B, we're gonna print hailstone 2, and just say, hey, hailstones are parallel, and not print anything more. Hailstone cross in the past of A and return false. Similarly, if U is negative, hailstones cross in the past of U. The past of U sounds like a pop song. The smell of you. How was it? That was a good song. I'm in love with the smell of... No, it was the smell of you. Yeah, it sounds a bit more sexual than I remember it, but okay. Look at that. We have some things. We need some new lines in here. Whoops. Just print a new line. And well, actually we could print the new line at the beginning because we are doing early termination there. So let's print the new line here. Okay. So the first ones are the ones that are crossing on the future. Awesome. Then these are parallel. No, these hailstones cross in the past of A. And this is the 19, 13, 30 and 20, 19, 15. Where is this thing? I said, sorry, I got a bit confused. 19, 13, 30. So let's look for that. 19, 13, 30 are these the first ones. I don't know why I had so much trouble looking at this. And the B is 20, 19, 15. Yeah, in the past for hailstone A. Awesome. And there's something for the past of hailstone B, which is... Oh, I said past of U, but it's actually past of B. 20, 25, 34. Yes. And 20, 19, 15? Yes. Okay, so the future and past checks are also working, it seems. And finally, we want to find the intersection X and Y and do check if they are in the given area that we want to check. So this is basically XY, right? We can even copy this thing and say let XY be this thing. Beautiful. And finally, the last check. So for the given input, we want to check if the things were between 7 and 27. Okay. So let's return simply if X is, how do we write this? How do I write equations? So this and X, I don't know if this is the first, like this sounds like a Yoda conditional. 7 is less than X, but this reads as a whole is like X is sandwiched between the 7 and the 27. So I kind of like that. And then Y also want to see if it is between those two. So this and Y less or equal to 27. We can return that. But let's put it in a Boolean. Let's inside and just return inside. And or well, if not inside, we're gonna print line hailstones cross outside the area. And all of those checks want to be floating point numbers. And this, what do you want to do, Clippy? Oh, ooh. Look at that fanciness. I don't know if it's actually better, but I mean, it looks neat. So okay, let's roll with what Clippy wants us to do. So finally, I want to print this number. So in the end, let's print line this thing. So if we run for the sample, yes, we find 2, which is what we expect. That's awesome. Now for running the actual inputs, we want to check a different area. So what is the area? With an X and Y position, at least this and at most this. Beautiful. So let's just put this thing on a variable and say area. Yeah, just area. The area contains, and here we can also say area contains, and we're gonna change this then to use these giant numbers. Beautiful and beautiful. So now if we should be able to run with input, but it's gonna be like super noisy because of all of the printing. So well, but it finished. I can clean up the printing later, but is this the correct answer for part 1? And it is, surprisingly it is. So floating point numbers worked and line intersections worked. So this was interesting on the mathematics side of things, I guess. I felt very, very rusty doing these kind of things, but we got it. And I think it's already a bit late, and I don't know if I will do part 2, but let's read what part 2 is about. Upon further analysis, it doesn't seem like any hailstones will naturally collide. It's up to you to fix that. Wow, what are we going to do? You find a rock on the ground nearby. While it seems extremely unlikely, if you throw it just right, you should be able to hit every hailstone in a single throw. What? You can use the probably magical winds to reach any integer position you like and to propel the rock at any integer velocity. Okay, always integers. Now including the set axis in your calculations, if you throw the rock at time 0, where do you need to be so that the rock perfectly collides with every hailstone? Due to probably magic inertia, the rock won't slow down or change direction when it collides with a hailstone. In the example above, you can achieve this by moving to position 24, 13, 10 and throwing the rock at velocity -3, 1 and 2. If you do this, you will hit every hailstone as follows. So okay, so if you're doing this and you do it in 3D, wow, you can collide every hailstone. What the hell? So this is another line that crosses all of the hailstone lines. What the actual? Okay, I will have to think about this. Above, each hailstone is identified by its initial position and its velocity. So does this thing collide like exactly like collision time 5 and collision position is gonna be this. So yeah, after 5 this is gonna be at exactly this position, and this one, for example, after 5 is 24 minus 3 times 5 is 15, so this is 9, yeah. 13 plus 5 is 18, 10 plus 5 times 2 is 10, so 10 plus 10 equals 20, so yeah, wow. Okay, above, each hailstone is identified by its initial position and its velocity. When the time and position of that hailstone's collision, then the time and position of that hailstone collision with your rock are given. Okay. After 1 nanosecond, the rock has exactly the same position as one of the hailstones, obliterating into dust. Another hailstone is smashed to bits 2 nanoseconds after that. After a total of 6 nanoseconds, all of the hailstones have been destroyed. So at time 0, the rock needs to be at x position 24, y position 13, and z position 10. Adding these 3 coordinates together produces 47. Don't add any coordinates from the rock's velocity. Determine the exact position and velocity the rock needs to have at time 0 so that it perfectly collides with every hailstone. What do you get if you add up x, y, and z coordinates of that initial position? Wow, this is such a weird puzzle. So you can make a line that intersects with, not only intersects with all of these lines, but also at the exact position, at the exact time that you want to, like, yeah, you throw something linearly, like a stone linearly, and it will catch every hailstone at a position. That is amazing. And how the hell do you find this kind of thing? How do you think about this? Because there are even like parallel lines in the thing that we have, but that doesn't matter. It's just a line that crosses them all. So this must be a line. Oh man, thinking about part 2 is going to take me some time, I think. And I don't think I will be able to do it now, so I would prefer to just clean up part 1 and commit it, and then keep part 2 like thinking about it in the back of my brain, to be honest. So let's clean up all the printing that we did. This printing, actually we can leave this as comments. Stones are parallel. Yeah, we can also ask this as join these 2 conditions. Collide in the past. And this is the intersection. The area, okay. We can put this outside, I guess. where do we put this? Maybe here. And if I also want to do this with sample inputs, we can do some stupid check, like say the area is going to be if the hailstones are less than, I don't know, 10, it's the sample. So let's write this thing. Well, else is going to be this thing. And on the sample, it goes from 7 to 27. Oh, I closed it. Like, okay. Sure. And that's it, I think. If you run this thing with the inputs, we get the same answer as before. Great. If we run with a sample, we get 2. We can copy this to the answers file. Day 24 is this. So now we can run check all and it should pass. Okay, great. And almost there. I would also add some little bit of math comments to this to make this a little bit more understandable. So also this, I would call it is sample, and yeah, area. I don't know if this contains is the nicest thing, but yeah, it's fine. It's fine. It's just to have like the check for the sample on like the tests. So okay. Let's copy some of the notes. So we can say that the equations for the 2D lines of both hailstones are this. So this is hailstone 1 and hailstone 2. Yes, something like that. Then we can say well, we can just put the formulas for T and U, which is what we get. And this is basically also what we wrote here. So okay. Solving for now I think the system of equations that for T and U is this, which also comes from this, I guess. So okay, it's a bit like rather ugly how we have these minus signs here, but I'm not sure how to change that. So for the intersection, let's say intersection point xy contained in both lines. T and U form a system of two equations. Cannot wrap this, so the system of two equations would be this basically. Which can be solved using, all the things that I closed can be good links. I guess these two line segments is the link probably that I want to give, or the Kramer's formula for explicit formulas, yeah, for small systems. Can be also solved using Kramer's formula. Kramer's rule, apparently, is called. Yes, which is the one that I copied. I think I copied, well, from both articles basically. But I think this one was, well, I don't know if it was better, but anyway, too many things in Wikipedia. Solved using Kramer's rule. Yeah, we can give the link there, and we can copy our solutions for T and U. Yeah, what an ugly thing. To be divided here. U is this. Maybe doing this. Okay. Yeah, not the prettiest thing, but okay. And yeah, then we can leave these comments, like when the denominator is 0 means that the hailstones are parallel. And like these comments are like explaining these different cases, so that's all right. And then we compute the intersection directly. So yeah, I think that is more or less what we want to see. See also, maybe see also this article, which is, I think, the better of the ones here. Okay. Beautiful. I don't know if this wants to live on, be on another, like extracted into a function maybe, that takes two hailstones. Could be. Hailstones collide, but also I would have to be passing this area, which is not very nice, I think. So let's leave it all inlined here. No problem. Everything on the main. So if we run, we should pass all the checks. That's great. We are going to basically add everything. Well, the README, no, discard these changes. Well, the answers file for sure, and all of this also. Okay, So add solution for day 24, part 1. And that will be it for this video, I think, because thinking about part 2, like, it is a single line that crosses everything, that crosses all these lines. So that already is very interesting. That the line crosses all the lines, it means, what does it mean? Well, it means that it intersects these things in 3D. It intersects all the lines in 3 dimensions. So for a single line in 3 dimensions, there are infinite lines, of course, that intersect it. They can come from any direction, but given 2 lines in 3D, that restricts, like, it's an interesting surface. Like, if you have 2 lines, for instance, like one like this and one like this, and they don't cross, they don't touch each other, you can think of all the lines that go through both, and it's like a curved surface. But those are 2 lines. If you then add another one, since that is a surface, I think, with 3 lines already, I think you will already have 3 lines that are not parallel, and maybe that don't intersect each other, so they are very different from each other. I think with that, we would already have, like, the solution be one single line, I think. And then once you find that single line, you want to find the initial position to intersect all of the hailstones. It's a difficult thing to think about, but I think I will have to kind of think it in the abstract, maybe with pen and paper, and see if I can come up with a solution for that. Because doing that, like, on the computer and typing doesn't seem like the most appropriate way of thinking about maths, I think. I also have, like, a board to write, which I find it, like, more pleasant than writing with a keyboard and writing math like this. So yeah, for part 1, I think is good enough as it is now. So let's do this and this, and do our usual thing of a little thumbnail. So this is day 24 already. We are almost there. And this was basically remembrance of old algebra. Was that the name of the 3-body problem? Remembrance of old Earth? Of Earth past. that was the name of the 3-body problem series. Just as paying homage to that, of Earth's past, of, yeah, kind of algebra's past, but it's kind of my past on university, and now I don't remember anything, but remembrance of university's past. So we can say that. Please, give me one of these. Remembrance of university's past. Yes, it will be a very appropriate title or thumbnail for this video. and maybe I should actually take a look at the notes that we have been writing, which are, I feel like, more interesting than the code itself. So yeah, that will be it as a thumbnail for this video, and that will be it for this video. So as usual, if you have been, thanks for watching, and remembrance, did I write this correctly? Remembrance. Is this correct? I don't even know now. Remembrance. Oh. Today I learned something new also of how to write. I don't have spell checking on the terminal, so remembrance of universities past. Okay, now that will be the thumbnail, and now it will be the end of the video. So as usual, if you have been, thanks for watching, and see you later. Bye bye. Hi cats. Bye.